Welcome back. This is Larry Benko, W0QE, and this video takes a look at inductors wound on powdered iron cores. The picture shown here has 6 different core types, some of which may be recognizable. But quickly, the red ones, or red ones with a gray on the one side and red on the other side, come from different manufacturers. That's the most common material, I believe, which is number 2, which is a permeability of 10. The all yellow ones, like this one and this one, are number 6 material, which has a permeability of 8. The blue and yellow ones, like these two, are permeability 3, which is a number 17 material. And less common are a solid blue one, which is a permeability of 20, a solid black one, which is a permeability of 6, and a solid light green one, which is a permeability of 30. All these fit in a category called powdered iron cores, which generally have permeabilities from about a little bit over 1 to as much as I believe about 40 at the limit. I excluded the number 26 material, which has a permeability of 75, because it's not suitable for RF. I made a bunch of measurements with several of these cores over a number of days, and I realized that I had way too much data for a single video, so I decided to back off and present the data for a single core that I wound with a lot of different configurations on that single core. And I believe from that we can learn probably more than we could from the larger amount of data. So before we get started with the actual data, let me show you what equipment I used and how I did this. The first 2 pieces of equipment I used were my 4170 impedance analyzer with a special adapter that I made for it, which is shown here, and a old LC meter that used to come from it was a kit. It was almost the old AADE kit before the gentleman died who ran the company. It's been pretty accurate at measuring inductance, and it measures inductance by increasing the frequency when the inductance is small. So, and it's proven to be very accurate. The 4170 is very accurate if I calibrate it carefully. And what I did was I decided I cut down a dual banana plug, and you can see the two grub screws that go in here and grab the wire. And all the tests I did were done with a 0.75 inch standard center to center distance, and this device plugged in. I calibrated the 4170 to exactly this point right here for a reference plane. And the third piece of equipment I used was a borrowed HP 4342A Q meter. And the Q meter is very nice because it can measure Qs that are pretty high pretty accurately, and it has a 1 inch spacing between the banana plugs. So what I did is I made a little adapter here on a thick piece of copper base soldered to this barrel adapter, and I plugged my inductor in between here. And between the 3 of those, I compared the measurements. The 4170 and the Q meter both measure Q. The 4170 does not measure Q high enough but that and the LC meter all measure inductance. So I continued to make all these measurements sporadically amongst all 3 instruments, just to make sure that I was making the same measurement everywhere. And the Q meter only reads inductance at various frequencies, and there's a little mark on this dial here you set it to, and then inductance can be read directly. Anything else you can only read, you have to do a calculation to figure out what the inductance value is. So with that being the case, I picked the current values. If you look in inductor books over the years, you'll notice that inductors are measured often at 790 kilohertz, 2.52 megahertz, 7.9 megahertz, 25.2 megahertz. Well, those are the standard numbers that the Q meter uses. You set there's a couple little ticks right here you set, and then that's the frequency you use based on the band selection. So this is pretty much what I used, and I think you'll find this to be pretty interesting. The results to be pretty interesting. Shown here is a very limited set of the data, which hopefully will not make things too confusing. And also the drawing, a little picture with how I made some connections to enable me to make these kinds of configurations. So what I have is 16 turns of number 14 wire wound on this T130 core, which is a 1.3 inch diameter core, and the wire is 1.63 millimeters in diameter, or number 14. And I wired some heavy wire or some copper straps, thin straps, from these solder points back here to the end. And by doing that, I could make several combinations of active number of turns, shorted turns, and whatever I needed to. And then later on, I peeled off the turns one by one. When I peeled them off, I didn't spread them back out. I just peeled them off and then wired directly to the end point. And then I combined the data, and then I deleted a whole bunch of the data to show what's going on here. So what we have in this configuration right here is a case where we have 4 active turns, 1, 2, 3, 4, and then from turn 4 we have a connection going back to the end, which bypasses all these turns. But we have this turn 5, actually shorted out by itself, and then these turns 5 through, or whatever, 6 through 16 are shorted out in mass. This is just, it was what I had available to do. So let's look now at these 5 different points. What they represent is 16 turns active, which is just this core here. Let's do this. We'll use a littler one. 16 turns active. Nothing shorted out. The inductance I got, I'm going to call, say, 3.04 microhenries. And I'm just using this data, this line of data. I could use any of the data lines. The numbers are not that far off. When I went to 15 turns, I unwound this one turn and I wired from here to here. Then when I went to 14 turns, I wound another turn off and went from here to here. When I went to 11 turns, wound all these turns off and wired directly to there, etc., etc. And if I look at these values, you have to ask yourself, do they follow the square law or not? The formula for ferrite cores and powdered iron cores is always something like some A sub L value, which is a base value, times N squared. I use the base value that comes with a T130-2 material, and it's 11 nanohenries. And I did the calculation here with the square term in there, and I get these values. We notice that this doesn't match very, very accurately, and it's getting closer as I add more turns. It actually gets pretty close if I get to 20 turns, but it underestimates the value everywhere else. And another way to say that is this is not going up. This is not going up as a square. Looking at it a little differently, here's a case where I have three different sets of data. These are not measured data. These are just manufactured data. The first one is using the Wheeler formula. The Wheeler formula was an approximation on empirical data. It is not a scientific formula, but it is a curve fit on measured data done by Harold Wheeler at the National Bureau of Standards, I believe in either 1939 or 40 or 41. He published several formulas, but this is the standard formula we see all the time for a single layer air core inductor. The radius squared times the number of turns squared in the numerator, and then the denominator is 9 times the radius of the turns plus 10 times the length. This 10 times the length piece is what takes away the square aspect of this, because as we add another turn, the denominator is changing. So what I did was I came up with a coil here, which was 0.986 inches in diameter, 10 turns per inch, and I did that so I would get exactly the same inductance with 16 turns. So here I have 16 turns on my mu equals 10 core, and this data right here is just this data right here. I made those line up. Then I artificially manufactured some super high permeability core, which is exactly the square of the turns ratio, and I came up with this constant to give me again 3.04 here. So for all 3 of these inductors with 16 turns on them, we have 3.04 microhenries. What happens as we go down to, say, 15 turns? At 15 turns, we don't see nearly as much of a change in the air. In the air core inductor. It drops from 3.04 to 2.81. In our powdered iron toroid, it drops from 3.04 to 2.72, and in a true square law fashion, it drops from 3.04 to 2.67. It turns out I tried to do some curve fitting. With mu equal 10, this follows a square law pretty nicely, except for the fact that the power is 1.5, so it's not really a square law. So if you take the turns to the 1.5 power times some constant, it follows it pretty well. None of the published data mentions anything about that for cores. I've experienced this over the years. If I put a fair number of turns on a powdered iron toroid, I get pretty good results from the formula, from this kind of a formula. If I put fewer turns on, my numbers are increasingly off, and we see that as we drop down. We see that we're getting we're dropping off at a different rate than the air core inductor does. However, the air core inductor is interesting in that it rises more than linearly for a while, and then it stabilizes. And you could kind of imagine how this works. If each turn on the air core inductor is only capable of coupling with the next adjacent, say, couple core turns, then you end up with, well, the first two couple pretty well, the first three couple pretty well, four couples maybe with 2 and 3, but not in 1. By the time I get to turn number 7, it couples maybe with 5 and 6 and 8 and 9. So as I start getting up here, the amount we add each time we add another turn becomes an equal number. And we see that because this stabilized at 0.23 microhenries additional inductance per turn. So anyways, the formula that's in the books for how to calculate these is just an approximation. The other thing that you need to consider is, in my case, I used a fractional piece of the toroid when I had a smaller number of turns. A person normally would use the bulk of the toroid. So if I had 8 turns I was in my inductor, I would spread them out over this distance. By having 8 turns down here, this core will have more inductance than if it's spread out. So squeezing the turns together increases the inductance. But nevertheless, this is interesting. It does not follow the square law, and it follows something in between, which kind of makes sense. The permeability here is 10. This is a permeability of virtually infinity, and this is a permeability of 1. There's no reason to believe that this isn't somewhere in between the two values. So let's just leave that at as for what it's worth. I'm not proposing a formula or anything, but I did do some tests with number 17 material, which has a permeability of 3, and it looked much more like the air core. And I did also a test with the permeability of 30 iron powder core, and it showed results a little bit more like this, when that's exactly what we would expect. Now let's look at the data a little bit differently. Let's look at the two lines which have 15 turns. The first one has 15 turns, turn 16 was removed, so it's just a straight 15-turn inductor, and then this turn is gone right up here. The second one has 15 turns active, but I shorted the last turn out, so I put a little put a little strap between here and here. So what happened? The first case we had 2.73 microhenries with a Q of 400. When we shorted the one turn, we went down to 2.33 microhenries and Q of 270. I'm pretty sure that everybody's looking at this is either going, wow, that's no big deal, or wow, that's a big deal. And I don't really know how to represent this correctly, but the inductance drop was fairly significant. The Q drop was fairly significant, but this is still not a bad inductor. Q of 270 is not a bad inductor. So having a shorted turn on this inductor is not the kiss of death. The inductor is not going to blow up. It's not going to overheat necessarily. It's got a Q of 270. It certainly is not as efficient as without the turn. So, as we've learned again in the past, air core inductors easily have shorted turns and don't seem to have an appreciable difference on the overall Q, although I don't have any data to show that right now. I've measured some stuff in the past that indicated that. And of course, a very high permeability transformer, a shorted turn is absolutely devastating to the transformer. Huge currents flow in that case. So here we are again, somewhere in the middle, and people who make statements like, well, you never have a shorted turn on a powdered iron core. A shorted turn here is not an unreasonable thing. Let's look at 14 turns. In 14 turns, I did it 2 different ways. So I have 14 turns with the turn 15 removed, and turns 15 and 16 removed. So I had just straight 14 turns and then a strap going to here. And that gave me a Q of 2.39 microhenries and an inductance of 2.39 microhenries and a Q of 390. Then when I shorted out, remember this data was not taken in this order. When I had 14 active turns with turns 15 and 16 shorted, the inductance dropped to 2.12 microhenries and a Q of 275. Then I played a game where I shorted out turns in the middle instead. The inductance drop was even more, and the Q dropped a little bit more still. I don't know what to read into this other than the fact that this kind of separated these turns from these turns by having some shorted in the middle. I guess I could imagine that since that was the case, these two, any coupling between this turn and this turn over here was less with these turns shorted than it would have been if, the turns were just all shorted at the end. But anyways, that's what you get. Again, the Q didn't drop drastically or anything else. 11 turns, same kind of a deal. We saw Q drop from 375 with no shorted turns. When 4 turns were shorted, it dropped to 280. And we can continue on down. Here, in this case, we have an error. Let me get rid of that. That's a mistake. It looks just like the 11-turn case. Sorry about that. In the 8-turn case, though, we have 3 turns. So let's color that a different color and look at it. All right. In this case, we see with the turns removed, 8 active turns only. So we have windings to here and then a heavy wire back. We see 1.11 microhenry and Q of 320. If turns 9 through 16 are left open, what we see is the inductance actually rises a little bit. The Q is still dropped somewhat. With the turns shorted, we see the inductance drops somewhat, and the Q is still the same as it was if it was open. But what we notice specifically is the resonant frequency of the inductor with just the bare turns was 135 megahertz. When we left the turns open, we ended up with a resonant frequency at 67.7 megahertz where it became capacitive, and then it became inductive again at 97.9, and this resonant frequency was lowered an awful lot. The shorted turn case, the resonant frequency was lowered, but not nearly as badly. We can see this type of thing very easily. So here we have the data for scan. It turned out to be, again, these numbers don't match the numbers in the error page, but this was the data for the case where we had the turns open. So we saw the resonant frequency drop down here to somewhere 67 megahertz or 68 megahertz, and somewhere here around 95 or something. Well, this is a different piece of data than the last one, but I picked the wrong graph. But nevertheless, what we're seeing is this is open turns, and this is a reduction. So this was an inductive up here. It became capacitive down here. It was an inductive up here, and went capacitive back down here again. And here's the Q. Now the Q goes up here on the 4170. So I did the same. I took the same data, brought it into SimSmith, and instead of the Q going negative because I did X over R, I played the game that a lot of people play, and it's the absolute value of the reactance. And in this case, what I have is 9 turns. Okay, this was 8 turns we were talking about before. This is 9 turns active with turns 9 through 16 shorted and open. So here we have the case L and Q, L1 and Q1 are shown. So this is with the turns, with the inductor with the turns open. Now let's look at the inductor with the turns shorted. We see the inductance drop here, although with the turns open, we see the inductance rising a lot faster and it becoming, the Q's lower, the Q stays higher here for a little while. I mean, you draw your own conclusions. The scary thing about leaving open turns, and a lot of open turns, is the fact that by leaving the turns open, you end up with these resonances, and if they come down far enough, they really start to affect the inductance, and they become a little scary. I made no measurements as far as what the open circuit voltage was at the end of those turns. That's, again, more data would need to be discovered. One thing that is very interesting here is, as we go down to a very small number of turns, look what happens. With the turns open, we see we have an inductance here of three turns open. We see we have an inductance of like 0.3 microhenries. With the turns shorted, we actually have a higher Q. The Q number rises. So we had a few turns here active, a bunch of turns just out open with no connection, and that was a lower Q than actually shorting out all that extra wire. So that's kind of an interesting observation. I found this data pretty interesting. The big thing I took away from this is the fact that the shorted turns aren't nearly as bad. I've got an amplifier here that was manufactured commercially. It runs legal limit plus some. Probably runs about 2,500 watts. I use it for testing. It has a powdered iron core for 80 and 160 meters in the output tank circuit. And it's a big, heavy, multiple powdered iron cores. And these multiple powdered iron cores have very large wire around them. I don't know how hot they get, but I can tell you in testing components and stuff, running 2,500 watts in this amplifier at those frequencies has not burned up that powdered iron core. And the shorted turns on the powdered iron core are there on 80 meters because the core is wound for 160, and they use a section of the turns for 80 meters. So anyways, hope you found this interesting. There's a lot of stuff you can do. SimSmith, which this was not primarily a video about SimSmith, but SimSmith is certainly capable of analyzing this data. I did not look at core loss. I did not look at a lot of different things, but I did look at a couple of the topics that people talk about regularly, specifically whether the turns ratio to inductance and how that works, and whether or not shorted turns are allowed. So I hope you find this interesting, and give me some feedback and let me know if you think I missed something or I should have included something, or if you disagree with anything I have to say. Thank you very much.